Thank you, Abramo. So first of all, I'd like to thank the organizer and the scientific committee for the excellent choice of speakers. So thank you for the invitation. I would like to talk about equisingularity, but over the real numbers. And for a global object. So the problem is related to what Terry talked about, but of course what we are able to do is quite modest and still in progress. So I will report on about this work with Nicolas Dutertre. We started many years ago, and there's still a lot of work to do. So let's start with our context. So I will recall a result of Renato, from the 1960s. So let's pick a real complex polynomial, whichever. And did prove that outside of a finite subset of values, that's not going to be the last one. Huh? So outside of a finite subset of values, the polynomial induce a smooth fiber bundle structure over the preimage of the complement of this finite subset of values. That is, I have a trivialization, local trivialization around any value outside this finite subset, and the projection map corresponds to the function f. So locally, the preimage of a neighborhood of one of these good values is just a product. A product, and the projection is given by the function f. The problem is just the result of Tom is qualitative. That is, there exists such a subset. Now, how do we find it? How do we pick these values at which the smooth type of a bundle of fibers is not constant? Well, I will, so BF stands for the bifurcation value, but I will prefer using either typical values for those which are not in this subset, or atypical values for those values which are in this subset. So this is the starting point of our work. And so equisingularity in this context will be to guarantee that we are far away from those atypical values. So either finding necessary condition, sufficient condition, whatever of this nature, but to guarantee that we are far away from these. So in order to substantiate what we try to do with Nicolas, I will speak a lot about what is known in the complex world, because there is a little bit known in the complex world. So we will start with as far as I'm aware, by the two-dimension, the plane result by Ha et Le. So this happened in the complex world for polynomial in two variables. And what do they prove? They prove that a value is typical if and only if the Euler characteristic is constant in a neighborhood of this value. So I don't know if practically it's easy to compute the Euler characteristic of the fibers of any plane complex polynomial, but at least the criterion is very simple. It's just a topological criterion. And this topological criterion tells you that actually you have smooth triviality. Well, this is the first result of this nature. So now let's, that's a result of 84. Okay. So now let's suppose we are working in the complex domain made in any dimension, n. So I can write my polynomial as the sum of its homogeneous part. And the top one will be of degree d, so this guy. And let us introduce a certain subset, which I denote sigma, so which is the projective varieties, which is defined as the vanishing of the d minus 1 term of the homogeneous development of the polynomial f, and the singular point of its homogeneous term of degree d. And I look at it as a subset of Cpn minus 1. So the title of the slide is Polynomial with Isolated Singularity at Infinity. What is this? Well, the polynomial f is said to have isolated singularities at infinity if this subset sigma is finite. In other words, if you want to look at it as an affine subset of Cn, then it's a finite union of lines, vector lines. So this definition was, I suppose, introduced by Adam Paruzinski. And so, so I will have to give a name to the projective closure of the level T. So let's call it xt. Let's denote by mu of t the total Milnor number of this projective hypersurface xt, which can be infinite. This is allowed. Key of t will denote the Euler characteristic of the affine hypersurface corresponding to the level T. Sorry. Well, one of the consequences of this definition is that for the regular level of the function f, when I close them, the only type of singularities that may appear at infinity will be isolated. Okay, this condition gives that. And then, which means that for such a point, for such a value, regular value t, the total Milnor number will be finite. For if there would happen that we have a non-isolated singularity for some level, then the corresponding Milnor number will be infinity. Anyway, so Paruzinski, in his work published in '95, gives a few equivalent conditions to decide whether the value, a given value, of the polynomial function is atypical or not. So he proved the following then, which is exactly in the flavor of the previous result of Ha-Henle. A value is typical if and only if the Euler characteristic of the affine hypersurface is constant nearby the value. If and only if the total Milnor number is a locally constant function at the given value, and if and only if Lagrange condition is satisfied by the polynomial f at the value. I will come later to define what is Lagrange condition. So, yes. Yes. Yes, of course. What is understood is just the polynomial is such that it has isolated singularity at infinity. Absolutely. Okay. So we went from polynomial in two variables, so which with certainty may only have isolated singularities at infinity because we just add up points at infinity. So it's a special case of this result. Then let's see what happened for general complex polynomial. And then we have to enter in the work of T-bar. So I'll be quick because otherwise I can spend 20 minutes on this and the talk is almost over. So now let's pick any polynomial. So what does T-bar is just to the projective closure of a level, he associates a sequence of integer numbers which are obtained as some sort of intersection polar multiplicities in a way which is similar to what Tessier did in a local case in the 70s. Okay, so T-bar then shows a few years after Parodzinski that I pick this time, well, to make it simple, just I pick a regular value. And I want to know if a regular value is typical or not. Oh, by the way, I should mention this because I didn't speak about this. But there are regular values which are not typical, fact. There exist atypical regular values. I give an example. I mean, it's always the same for those who. So this Bruton example, it's a very complicated example, two monomials degree 3. This one. So you're going to see that the critical locus, if you do the math, the critical locus of this function is empty. And you can check, when you're going to check that the t level is irreducible if t is non-zero. And of course, at 0, there are two irreducible components. Okay? So I got the line and the hyperbola. So those things certainly, around the value 0, I cannot have a bundle structure for the pencil of levels. No, this does not happen. So just to say that the hypothesis I put in the statement is not trivial. This happened. And the whole issue with this business of looking for typical values come from exactly those ones. The fact that there may be regular values which are atypical. We know in the complex world that if I have a critical value, there are the corresponding level as singularities. And so it must be already an atypical value. So T-bar proved that if the sequence of numbers, which depends on the level above, is locally constant at C, then the value is typical. He does prove something which is more interesting, that actually the constant C, the local constant C of this family of numbers is equivalent to have, again, this Lagrange condition satisfied at the value. So now I think we should be ready to speak about what is Lagrange condition. So let's pick any function which is at least C1, real or complex, whatever. Okay? And by Nablage, I will denote the Euclidean gradient. So I will say that a function g satisfies Lagrange condition at a given value if, well, there is a definition over there, but what it does say is just that when it goes to infinity and in a neighborhood of the considered value, then the gradient is not too small. It may vanish, but not too fast. That's what it says. Okay? So it may vanish at most of order 1 over to the distance to the origin when x tends to infinity and the function along such a sequence converge to 0. If it goes to 0 faster than this, then the value doesn't satisfy Lagrange condition. And I will call, it's not me, let's call that a value C which does not satisfy such condition will be called an asymptotic critical value. Okay? So any level C of the function which is singular and with a non-compact critical locus will fail this condition. Of course, because the gradient will be 0 along a sequence that goes to infinity. In particular, the value 0 of this example is a value of this function at which the function is not Lagrange. Okay. So now more notation. What's the relation between values at which a function is not Lagrange and atypical values of such a function? So I will write down K0 of G, which the critical values of the function. And K infinity of G will be the set of asymptotic critical values of the function, that is, those at which Lagrange condition fails. And then there is a result which has many authors, I mean about 2 lines of authors over from the early 90s to the early 2000s. And now I'm going to be a little bit more general without saying what I'm talking about. So assume now that you have a globally definable function. Sorry, I have a function which is globally definable in a nominal structure, and I probably forget that it is C1. If you don't know what it is, you can think of a real polynomial. That's going to do it. So the first statement of in this class of, so I forget C2, C1, sorry. You can ask here that such a G is C1. So the first thing is just the union of the two or both subset of values, the critical values and the asymptotic critical values, is finite. But more interestingly is the second condition. It's just if the function is ck plus 1, then outside the preimage of this subset, the function g induces a ck fiber bundle structure. In other words, if I was looking for the ck atypical values of the function g, they would be contained in this set, in this subset kg. So in particular, it proves that the set of value at which the topology of the ck type of the pencil of level change is finite. Well, life being what it is in general, this guy, the atypical values set of atypical values is smaller than this subset. So now let's come to some result in the real world. And let's start with, again, in the plane. So I pick a real polynomial in 2 variables. Chi of t is still the Euler characteristic of the level. And so Tibar and Daria, they prove in 99 that a value is typical if and only if the Euler characteristic is constant nearby the value, but it's not enough. You need that there is no splitting in C. And what does it mean? It means I cannot have a phenomenon like this. So for instance, here I have a collection of fibers, C plus epsilon, a connected component of a level C plus epsilon of the function, or C minus epsilon, epsilon. And then when epsilon tends to 0, these produce two connected components. This is a splitting. So this is not allowed. This phenomenon is not allowed. And there is another one, so there is something which is equivalent to this. There is no vanishing. That is, you don't have a component of either the level C plus epsilon when epsilon tends to 0 or C minus epsilon when epsilon tends to 0 that goes to infinity. That is, that's vanishing. That is, I don't have something like this. Oh, no. Let's put it this way. And I would have here. And here I would have C. So here would be a produce at C a vanishing component. That is, even if I ask that the number of connected components of the level C, of the level, is constant nearby C, is not enough, because I can have a vanishing which is compensated by a splitting. And so one component disappears, another one appears. So this is not good enough. So what they require is neither of the situation occur. I mean, if you have constancy over the characteristic and there is no splitting, then it's the same having the other one. It's exactly the same. And these things of no splitting and no vanishing is something that's really a real phenomenon. Those things do not happen in a complex world. So now, okay. So I've spoken of the Euler characteristic. If we think about Euler characteristic and we think about real world, we're going to think about Gauss Bonnet formula. So I pick a hypersurface which is connected, oriented. So nu H is going to be the Gauss map, that is the orientation. Key H of X will be the Gauss-Kronecker curvature at X of H. And key of H, that is the integral over H of this Gauss-Kronecker curvature, will be the total curvature of H, if it exists. It may not exist. Maybe infinite. And Gauss Bonnet said the following. He said that if H is compact, then total Gauss-Kronecker curvature is the same as the Euler characteristic. That is, the same means, well, there is a constant which depends only on the dimension. So it's the same. Okay. A problem is just when we're dealing with a polynomial, even real ones, levels are not necessarily compact. So Gauss Bonnet formula is not true, at least not true as such. So I'm going to present one of Duterre's formula. So let's pick a regular level of the polynomial. Okay, and so we may have many connected components, but I will orientate. The orientation will be given by the gradient of the function. So Nicolas has a formula to describe a Gauss Bonnet defect in the case of non-compact level. So you can have, like before, you're going to have that the total Gauss curvature, which in this case is well defined, it's finite number, it's an exercise, is, so here you see, what am I doing? So here we have the Gauss Bonnet part, but we need something else because we are maybe in a non-compact setting. And then there is this term here, so which is the average of the Euler characteristic of any hyperplane cut of V. So this is what happens when the ambient space has odd dimension. And when it has even dimension, you get something of the similar type, in more complicated. But still, they both they both are Gauss Bonnet formula. So what I want to talk about, why I'm talking about this, is because, as we have seen in the complex world, an equisingularity criterion a value will be typical if, at least, of course, the Euler characteristic must be constant. In the complex world, such a guy would just be an integer times the volume of the projective space, and that's it. It's not the case in the real world. I mean, independently of the nearby level. Here, if v varies with the level of the function, this function will vary. I mean, most likely. So we cannot expect in the real case when I am at a typical point, these guys stay constant. We should not expect this. So this we get, and so what we have to understand is this. So either we understand this or we understand this, one of them, because it's the same information. So now, let's again a nice real function. So that is a globally definable C2 in a nominal structure. You can think of a real polynomial. So now we'll write kt of x, the Gauss curvature of the level ft at x. Of course, the levels are oriented by the gradient, and then you can try to do this for a polynomial. You pick a regular value, which is in the image. So the total curvature is well defined. That is a finite number. Even if, though a priori you integrate over a non-compact object, it does exist. And the second, that even if you integrate the absolute value of the Gauss-Kronecker curvature, it is also well defined. And it's just an application of the change of variable formula because you get a map over Sn minus 1, whose fibers are genetically finite, and that's it. And uniformly bounded. So that's why it works. And this new term I will call total absolute Gauss-Kronecker curvature. It's the integrand of the absolute value. It's not the absolute value of the total integrand. These are different objects. So this object is actually what is something which is quite close of a complex object, because there is no cancellation, and that's what happened in a complex world. Okay, so why speaking about this? I speak about this because I can define the corresponding function, total curvature and total absolute curvature. And what we can prove within the hypothesis I have given is just the total absolute curvature if the if the total absolute curvature is continuous at a value, then so is the total curvature. In other words, if you got polar curves, because that's what curvature is about, I'm counting polar curves, and this one counts the number of branches of a given polar curves. That's what it curves. And I integrate this number over Sn minus 1. The other one, they count things with signs, plus or minus. So this means that if when I go at infinity nearby the level C, there's no new polar curves, then this one will not see it as well. I will not have modification in this one. But what is more interesting is just actually the total absolute curvature is discontinuous at most at finitely many points. Like we know for the complex world, we have finitely many critical values, and when we're working with isolated singularities, they will be characterized by the presence of pencil of polar curves along which the function tends to the given value. When I'm talking about pencil, I'm talking about open pencil. So it is something of this flavor, and that's what this total absolute curvature measure. Doesn't count sign, doesn't count compensation. Yes, wow. I proved this. It's not very complicated, some time ago. Now, why these total curvature functions may be of interest? Because since they contain an information about the way the level bends, they might detect, to some extent, a change in the nature of a level, like it happens in the complex world. So, let's pick again a nice function in a nice category of functions, say, and if you don't know what I'm talking about, just think about a real polynomial. It's good enough. So there is a, well, as per se, Coste de la Puente didn't prove what I'm going to say. What I'm going to say they proved. But it's an easy exercise to show that what they did allows to say that. So you pick a real polynomial, then a value is typical if and only if regular value. Yeah, I forget to say. Regular value here, if and if the total curvature function is continuous at C. That is the one that is counted with signs. Well, actually, it works for this sort of function above, because their criterion is generalized as well for such functions. What I did a little bit later, so you can think of a polynomial. I have defined previously what is a polynomial with isolated singularities at infinity. I gave it in a complex world, but the definition makes sense as well in the real world. So you pick such polynomial. So there is an analog definition for general function like those ones, but it takes a bit of time to define. So what I did prove was that if the total curvature function is continuous, then the value is typical, starting with a regular value. In other words, if there is no polar curves which accumulate when I go to infinity along which the function tends to C, then it's okay. I can find a trivialization. It's a very reasonable statement. If you think of it in these terms, there is no surprise here. In general, in the real world, what you're going to have trivialization implies certain conditions. Finding sufficient condition which guarantees trivialization, it's much harder. So this result in its own is a very strange object. Of course, there is a very strange hypothesis, which is this one, which is a very strong hypothesis. So now, I can speak of the main result. So I got 5 minutes left, it's enough. So what I tried to do up to now was to some extent justify that those total curvature functions, the total one and the total absolute ones, are of interest if we want to investigate real equisingularity nearby a value of a function. So you pick C1 function. Well, you pick a regular value, and we will say that the function is spherical at infinity if, when I pick a sequence of points that goes to infinity, along which the function tends to the given value, then at the limit, the normalized gradient can only have is spherical. Let's put it this way. So I have infinity here, so which is my nice, you can think of a sphere. And I go there, And my sequence here goes to a certain point. Then the gradient along this sequence, the normalized gradient, will be orthogonal. That's why I'm asking. Okay? I know this is weird. And there is a set, the values at which the function is not spherical at infinity. So what I proved with Didier Kunto many years ago, we didn't call it this way in this time, but anyhow, is just if you have one of these functions we are working with, then for your polynomial, then first, the set of value at which the function is not spherical at infinity is contained in the set of asymptotic critical values. In other words, Malgrange condition implies sphericalness at infinity. That's what it says. So this condition is weaker than Malgrange, and it is a different condition. The converse is not true. So in particular, that guarantees that we can trivialize. I'm going too fast. So now if I pick a value which is neither critical and at which the function is spherical at infinity, then the function has a bundle structure. The value is typical. Let's put it this way. Okay? I must point out that there exists sufficient condition of trivialization which are much better than this one. But with regards to what we're able to prove with Nicolas, we don't know how to use this condition, and it's probably not true. So what is it we prove? So pick one of these good functions, for instance, real polynomial. Let's consider a regular value. Then what we prove is just this. If the function is spherical at infinity, then the total absolute curvature is continuous. That is, there is no pencil of polar curves that goes to infinity and along which the function tends to C, which should say that I have equisingularity, if we think with analogy to the complex world. Converse not true general, of course. You look at this function as a function of C3. The total curvature function is constant equal to 0. So it means that if you want to find equisingularity criterion, you're going to have to investigate higher order curvature, which fits the result of T-bar because he used a whole collection of exactly n numbers to describe, to give an invariant whose constancy guarantees the typicalness. So, and that's what I say, so the continuity of this one does not imply necessarily typicalness. In particular, when it is constant equal to 0. But so far we took us it's not that we see each other very much, very often, but it took us some time just to prove this. There have been improvement on this problem, and I expect that Nicolas might speak about it in, let's say in July, somewhere in São Paulo state, a little bit inside. So in São Carlos, it's one of the topics he may talk about. So the progress we did on this topic. I'm about to be finished, and so I use funny words in this talk, especially those ones. globally definable, polynomial band-bounded, etc. So now, Marcelo explained that he already advertised what I'm going to talk about this morning. Yeah, most important. If you want to know, you don't have to. If you want to know a little bit more about those strange notions, well, there might be a way in May in Fortaleza. So we are organizing a school of real geometry. So there are different topics. And one of them will be an introduction to a minimal structure, which should explain, at least give a definition, explain, I don't know, give a definition of what is definable in a minimal structure and what is polynomially bounded. And if interested, there is a website, and you can even write us. Thank you very much for the attention.